Okay, lesson 3, nuclear equations. This one's going to be making you look like a boss when it comes to science. The level of mathematics required is that of about a 6-year-old, but it just looks trickier than it really is. So last lesson we learnt about the 3 types of radioactivity, alpha, beta and gamma. And we're going to look now what that does to the particles that they're part of. So let's look at the equation first for alpha. So what we saw there was an alpha particle, and we can write that as alpha 4, 2. Because if you remember, it was 2 protons, 2 neutrons. So alpha 4, 2. You might also see it written as He 4, 2, because that is just a naked helium ion. It hasn't got its electrons, it's just the nucleus taken from it. So occasionally you'll see it written as 4, 2, and if you're being absolutely correct about it, plus 2 there. But for most parts, you'll see it written with the symbol 4, 2, alpha. So, let's have a look. Let's take an isotope like uranium 82, if I remember correctly. I've got to get the numbers right on this. Let me just look it up. 238, I think I'm after. Uranium 238. Let's just quick Google it. Pretty sure it's 80 or 82. Uranium 235 is the bang one. Decay product, thorium 2. Yeah, we'll go with that. And the proton number is... Let's have a quick look. Hmm, 92. I was wrong. So 23892. There we go. There it is, decaying by alpha. And losing a couple of things on the way. So we had, try that again, 23892 uranium. 23892. And it's going to undergo radioactive decay. So it's going to decay. Now, if we're losing 4, 2, we're going to subtract -4 from the top. We're losing 4 things. And we're losing 2 of those as protons. So the new atomic mass is going to be 2, 3, 4. And the new atomic number is going to be 90. And that gives us a new element called thorium. And to balance the equation, just like a chemical equation, we're going to have the alpha 4, 2. So I told you the maths is really easy. It's just the symbols and memorising things. Now in exams you're always given most of these details. You'll never be expected to remember, apart from obviously remembering that an alpha is a 4, 2. So that's the first one. That's the alpha decay. Next one. Let's do beta decay. Now if you remember, in beta decay we saw that a neutron can decay into a proton and an electron. So let's have a look at what effect that has. There is a isotope of carbon called carbon-14. It's used, we'll talk about this later, it's used for radiocarbon dating. So it's naturally occurring, 1 in a million atoms of it are that, and it undergoes a beta decay. So we draw the arrow. This time, we're not necessarily losing. We've gone from a neutron to a proton. So the mass hasn't changed, it's still 14. But we have gone up by 1 proton. My neutron has turned into that. So we've gone to number 7, which is nitrogen gas. And we have to show the balance, so we create an electron. And again, you might see it written like this, beta -1, 0. And again, mathematically, 14 add 0 is 14, boom. And 7 add -1 is 6. So that's a beta decay. The last one, by far the easiest, gamma. Gamma was an electromagnetic wave. It has a mass of 0, a charge of 0. So if we take a radioactive isotope, let's take, now my brain's gone completely out. So I want to say sodium. 11, and it's completely got 23, I think. Then if it undergoes a decay, it stays the same. There is no effect. If my cup of tea goes cold, I don't lose the water out of my cup of tea. We just create a gamma 0, 0. So again, mathematically, all adds up, and that is balancing equations and radioactive equations. Really easy. This is on the next page after that last page of page 44. So this is page 45. So I'd copy those in. I'll put it in the top. Page 45. It's a short one, this. Have a go at the examples. Copy them in your book. Make sure you understand. Any questions, put them in the comments.